Welcome to Teaching with Technology in Undergraduate Mathematics. My name's Ami Mamolo, and you're tuning into choosing and using online teaching materials. I'm speaking with Parker Glynn-Adey and Miroslav Lovric, who are here today to help synthesize key ideas from Activity 3, Computational Modeling as a Teaching Aid.
Using computational modeling to teach mathematics isn't exactly a new strategy, but it's gotten new life recently. Can you two say a bit about that?
True, it is not a new strategy. The emergence of every new communication technology was viewed as an opportunity to modify teaching strategies. This happened with radio and television. In the late 1960s, with the development of the local programming language, Seymour Papert introduced ideas about play and experimentation using computers, both of which are important components of learning. The ideas were there, but unfortunately, we had to wait until the technology became more widespread to vast segments of population, and affordable, meaning cheap or free.
Today, for instance, we enjoy the convenience of Jupyter notebooks in coding with Python. Instructors have opportunities to pick between a wide variety of platforms, which are either free or their university subscribes to them. This makes accessing coding tools free for their students. Of course, Python is only one of the myriad languages that we can use in computational modeling. In these modules, we use it to illustrate the ideas we develop. However, the teaching strategies, pedagogical considerations that we discuss apply to a wide range of available computational modeling softwares.
So, for instructors who are new to using Python, what kind of time investment is there to learn the software well enough to create scripts that you could bring into your lectures?
We can rightly claim that most, if not all, mathematicians and math instructors are familiar with coding, having used at the minimum the math typesetting language LaTeX. Having this initial experience guarantees that the steep learning curve for picking up Python syntax will actually be quite short. After that, preparation demands a small amount of time. All that an instructor needs to do is become familiar with the commands with a specific purpose that they plan to use in class, such as working with matrices and vectors, or functions, or probabilities. Of course, there are other concerns. Is this effective pedagogy? Is this the right software for this purpose? However, I just want to say that the Python learning curve is not a major obstacle.
I agree. There is time investment, but the return on it makes it worthwhile. Python is versatile and easy to adapt and use. Often when we look for a specific ready-made applet, it is not there. Or what we do find doesn't do exactly what we need, and we give up. With coding, it's different. We might not be able to find the exact code we need, but it's easy to find something that's close enough. Borrow it and adapt for the use in our classroom. By the way, this is so common in programming. Rarely, if ever, does one start a programming task from a blank slate.
What would you say are some of the things Python does particularly well in the service of teaching mathematics?
First of all, Python extends what can be done in a lecture. In mathematics, there are a number of situations where you have to apply an algorithm, meaning you have to do heavy calculations, such as the Euler's method. In lectures, it is impossible or impractical to do more than 2 or 3 steps of any iterative method. You do it so that students understand how and why such a method works.
Doing 2 or 3 examples on the board as a chalk and talk presentation is not fully satisfying. It's not realistic. No one ever uses 3 steps of Euler's method in any actual application. In real-world situations, people are doing this on computers. In order to obtain useful results, Euler's method or other algorithms need to be run for 100, 1,000, or 100,000 iterations.
As well, to really do anything with Euler's method, we need to have experience with and know how to modify a differential equation, change the initial conditions, adjust the number of steps, and so on. Pencil and paper cannot help us here.
You have to have some kind of tool that allows you to calculate many steps and create a graph or some other appropriate output, which then students can interpret in terms of, say, a specific model. You want a conclusion like the population plateaus at such and such a value, and the fact that you see an answer allows you to discuss its meaning.
Coding also shows the power of combining things. Students learned about theory, they know what they're supposed to get, and now they can see that they get what they're supposed to get. It becomes tangible. It is a powerful way to bring math theory and practice together.
Do you have other examples of topics that have been beneficial to demonstrate with Python?
As I mentioned, Python can be used for any iterative method, such as bisection or Newton's method for solving equations. Beyond that, it can also be used to illustrate important concepts, such as series of numbers, or Taylor polynomials, or Riemann sums. In terms of what other topics you can choose, whatever is computationally heavy, not just in calculus, but say also in algebra. Very often we are stuck on calculations, and because we make mistakes, too much time is devoted to calculations by hand. Some of these calculations could be replaced by Python. The other aspect is that Python provides various kinds of visualizations which are hard or sometimes impossible to obtain by hand.
Yeah, another place that I use coding in a demonstration context is my Calculus for Management course. It is a chapter of probability, and things in probability are only interesting if you do them a lot. Say if you toss a coin 1,000 times. On average, the coin will land heads 500 times and tails 500 times. But I don't have time in lecture to toss a coin 1,000 times, so I use Python to do large sample size trials.
How closely does the code align with the mathematics? And are there any tips instructors should keep in mind to help bridge the gap between the math that students need to know and the code that's used to demonstrate the math?
Well, Amy, there are two aspects to this question. One relates to the technical side, the way we code, and the other is what comes before we start to code. I'm going to talk about the technical side. When coding, it helps when you name the variables appropriately, and in general, when you make the code consistent in terms of notation with the lecture notes and textbook. This way, by removing potential technical and non-conceptual obstacles, we can keep our students on task and keep their motivation high.
The other aspect is to practice repackaging a piece of mathematics so that it can be put into code. For instance, how do we use a loop to compute the sum of 10,000 terms of a series? Or how do we make sure that the code does not get stuck by encountering the square root of a negative number or division by 0? Or we need to figure out how to translate the iterations of the Euler's method into Python code. This process of repackaging is the bridge between coding and mathematics, and it is mathematics.
Coding is a very useful tool for understanding the long-term behavior of algorithms. Coding does not replace conceptual understanding of mathematical algorithms, but supplants conceptual understanding and extends what we can do in lecture.
This brings us to the end of our synthesis of Activity 3, Computational Modeling as a Teaching Aid. Thinking back over our conversation, what stands out for me is that Python seems to be quite a versatile tool that helps students see how things work out for large numbers of trials or large iterations of algorithms, and with real-world techniques. There is a time investment involved in repackaging and aligning a piece of mathematics with its computational model and code, and the potential benefits for developing student understanding make this investment worthwhile. We hope you've enjoyed exploring these ideas with us. To learn more about how Python can be used to extend teaching and learning opportunities for students, be sure to check out our module, Computational Modeling in Undergraduate Mathematics.
Thank you, Parker and Miroslav, for joining me today. I'm Ami Mamolo, and thank you very much for tuning in to Teaching with Technology in Undergraduate Mathematics.